Okay, so this is going to be a recording for our last two chapters for BUS202, which are chapter 8, in which we're going to be talking about confidence interval estimations, and chapter 9, which is we're going to talk a little bit more about hypothesis testing and some of the procedures, some of the protocols that go in that are associated with that. Okay. Um, So coming back, looking at our confidence interval estimations. So what we're going to talk about, or what we're going to discuss in this, is really this whole idea of being able to construct and interpret a confidence interval estimates for the population mean and the population proportion. All right. So remember what we have is really two things we're working with. One is going to be a population of some size. It could be of any, we don't put a requirement around that. We don't know what that is. And the characteristics we're looking for is going to be the mean, right, which is really kind of, as we said, our kind of our central, kind of a central point, the area around which values will accumulate, and a proportion, which is what percentage of the overall population is of a particular has a particular characteristic. All right, so we're going to talk about how do we deal with that for the population, because don't forget we're not the our challenge in statistics is we know we're not going to count everything. So we're not going to count the entire population. So what can we do to be able to construct confidence intervals to give us an evaluation of what the population mean is versus and also what the population proportion will be. All right. So going back, we talked about statistical inference, and the fundamental thing to remember about statistical inference is that it's our objective is to make an inference about unknown populations based upon the data that we contain or the information that is contained within a sample. All right. So the idea is what we're going to do is we have a population. We draw a sample or set of samples from that population, do an analysis of that, and then use the results of that to make an inference about the population, make an inference about the characteristics of the overall population based upon our sample. So part of what we're going to talk about here is, how we're going to use sample statistics, summaries calculated from our sample data, to answer questions about our unknown population parameters. All right, so we're talking around. So in this case, what we're going to talk about, the population mean versus the sample mean, and we're going to talk about the population proportion versus the sample proportion. So as we kind of have, one of the things we've as we've been going through this course and we've been talking about different things, one of the things we've learned is that the sample statistics are probably going to be their best estimates of unknown population parameter values. Or we have our best tool or our best estimate of what that is going to be take a sample and use that, apply the results of the sample analysis to be able to apply it against the overall population with some degree of confidence. Therefore, our sample statistics are point estimates of population parameters. All right, so we can estimate we can take a point estimate from a sample, for both the mean and for proportion, which is represented here, and use that to develop an estimate of what its matching population parameter might be. All right. Once again, there's degrees of uncertainty around this because we're not absolutely, we're not going to be absolutely certain about everything because we're not going to count everything. All right, but what we are going to proceed with is this idea of we can use the sample and the information we get, what we derive from our analysis of the sample, is going to be a basis for which we can make um, a description or make a statement with different degrees of confidence about what we think um, the characteristics are, or the mean and proportion for the overall population would be. All right, so estimation is it's a technique where we build intervals, we call them confidence intervals, around point estimates. So what we'll do is we'll take samples, um, do some analysis on the sample, which should give us a point estimates, and then use that as a basis to estimate our unknown population parameters with the proviso, or as I like to call it, the weasel clause, that there's a degree of confidence around it. So there's not going to be anything absolute. So once again, from a decision-making perspective, one of the things we have to take a look at is going to be, okay, what is this? What is this degree of confidence that we need to weigh or need to consider? All right. So the confidence, we have two situations, two scenarios here, two approaches we can take. Right? So one is going to be if we know what the standard deviation is of the population versus situations where we do not know what the standard deviation of the population might be. Right? So we use the confidence intervals. We can calculate confidence intervals with these two scenarios. All right, and what we call the confidence intervals for the population proportion, which is our pi symbol here. All right, so this is the population. So this symbolizes the population mean and the population proportion. Okay. So the general formula, as we're looking at this, is from a general perspective. What we're doing is we're going to first calculate our point estimate, plus or minus what we call the critical value. All right, at times the standard error. All right, so the point estimate is, as we said, that is the sample statistic that we're going to use to do our estimate of the population parameter of interest. All right, so if we're going to do the mean, we'll do a sample. We'll take a sample. We will calculate the mean for that sample, and then apply it around the population to make an estimate of what the population is with a qualification of our our critical value and our standard error. And what it is, it's also a plus or minus. All right. So what happens is we're going to be talking about, you know, it, things we're going to be explaining, or we're going to be using our basis of explaining a range of values, either plus or minus. All right. So we'll talk about confidence intervals. So there's really two different approaches. One is going to be for the population mean, and then the two scenarios were going to be if we know the standard deviation versus if we don't know the standard deviation. And then we have also a calculation around the population proportion. So this is the formula. All right, so for the confidence intervals for the mean of the population, what the standard deviation is known. So a couple things. Our assumptions, we put a stake in the ground, is number one, we know what the standard deviation is. Number two, and this is an important assumption, is that the population is normally distributed. All right, because what happens is if we have a normally distributed population, what that does that enables us to be able to make estimates, or be able to make statements based upon the fact that the shape of the curve is that it's an equal distribution on both sides of a certain height. And then the third thing is that if the population is not normal, all right, so ideally we'd like to have a normal population, but there's also, could be situations where the population is not normal. All right, so we'll talk a little bit about that, where you could see a skew. All right, and there's ways we can compensate for that, basically by using a larger sample size. If I use a larger sample size, in fact, what I can do is kind of pump up our basically pump up our evaluation, what we're using as our sample size, which to a degree will make be able to evaluate it of something that's more normal, something normal like. It's not. We know it's not normal, but it will give us. It'll be able to compensate, so we can use the approaches, the same approaches we would use if assuming that if we were dealing with a normal population. All right, so it's the mean. So as we see here, it's the mean, the point estimate of the mean. All right, plus our z distribution, which is the normal distribution for the probability of the probability is divided by 2, because what happens is this is actually, if you look at this, what will happen is this will actually deal with the data that's in the tails of the curve. All right, so what we'll do is we calculate a probability. What we'll do is we will then divide it by 2, and then one would represent the one tail, and one would represent the other tail. Right. Once again, we're dealing with the shape of our normal curve. All right, so as we see here, here's kind of an example pictorially. We're looking for a 95% interview. We're looking for a 95% confidence interval. All right, so our deviation is going to be so 95% interval. So it's 0.05 is 1 minus is 0.05. All right, we divide that by 2. As you can see, what we're also using here is we're also going to convert the x values into z values. So once again, the z values relate back to the normal distribution. So it's the approach. You said it's a conversion of our the normal curve conversion such that the mean is at 0. All right, and assuming that this is that the shape is correct, then what we can do is we can take our 5 and divide it by 2, which is actually 0.25. So each tail for the upper confidence level and the lower confidence level. If we look it up in our z chart, we will see it's 1.96. All right, so this actually will be positive 1.96. This will be negative 1.96 for the lower level. All right, so we're using some of the stuff we've talked about, before around this idea of applying the z calculations, which assume or is predicated on the assumption that we have a normal distribution. All right, so these are the common levels. So actually, this is all we can look at this as we look at our values here. 1.96, 95%. If you see, this is actually already done in a table, so we can actually use a table for this. All right, so the commonly used values are going to be 90%, 95%, or 99%. All right, and then what we will see is this is the z value associated with it. So a 95% confidence interval will translate to a 1.96 z value. All right, which is so it'll be a plus 1.96, on the left, on the right side of the curve, and a minus 1.96 on the left side of the curve, left side being lower confidence interval, Z being the upper confidence interval. All right, so we'll use an example. So we'll use kind of an example to illustrate this. So we have a sample of 11 circuits from a normal to large normal population has a mean resistance of 2.20 ohms. All right, and we know from past testing that the population standard deviation is 0.35. So we know the standard deviation. All right, so we're going to determine a 95% confidence interval for the true mean resistance of the population. Okay, so what we have is our mean. We've done our sample mean of 2.20, which is our X bar here. And then we have our plus minus the Z value, which is 1.96. The standard deviation is 0.35. Divide that when we do the arithmetic on this. And what we will see is that our distribution is between 1.9932 and 2.4068. So our interpretation of this is we're 95% confident that the true mean resistance is somewhere between 1.992 and 2.4068 ohms. All right, so you note we're not saying definitively that we know that it's this. We're saying, okay, we are 95% confident within that. Now the thing is, it's interesting is that the true mean may not actually be in that interval. All right, so we don't know if the true mean is actually in there, but what we can say is 95% of the intervals formed in this fashion will contain the true mean. All right, so then once again, it's as much the interpretation of what we do with this and the assumption of a lot of this is once again predicated on the assumption of risk. And it's depending upon, obviously, some situations you could look at this and say, yeah, that's perfectly acceptable. Versus, if you're in a scenario where when you run into this, the outcome is, potentially catastrophic, maybe you want to be more than 95% confident. Or maybe you want to be 99% confident, or plus. All right, so we do these calculations, and we will apply them in decision making situations. But basically these numbers are just some our input to our decision making process. So the evaluation, estimation of risk assumption. Risk evaluation is really kind of, we take these numbers and apply them in a fashion to be able to do this evaluation. Right. Now, what we talked about is this idea of, okay, if we know standard deviation, that's the approach we would take. However, for the most part, the question is, how many times are we going to know what the standard deviation is? Right, so let's look at that situation. All right, do we really ever know what the standard deviation is? And the answer is probably not. In the real world, you don't, we usually don't have that type of information at our disposal. All right, so a lot of these situations are going to be, we're going to deal with, we're going to do this creation of a confidence interval, evaluating the population mean, where we don't know what the standard deviation is. Okay, so what we can do is, we can substitute, if we don't know the standard deviation, we can create a sample or an estimate, or we can do our basis of using a sample standard deviation, which we'll call S. Now the problem is what this means is that once again we're dealing with uncertainty, so things are going to be a little bit more uncertain because this variable, the standard deviation, it's a sample deviation. It will be variable from sample to sample. It's not going to be the same thing every time. So to compensate for that, we're going to use something we call a t-distribution instead of the normal distribution, which allows us to compensate for this. All right. So in this case, in working, in working with this scenario is, we don't know the population standard deviation, and that the data is the data in the population is normally distributed. So in that case, we use something called the student's t-distribution. All right. So basically, it's the same thing where we're going to be using our point estimate as our baseline, and then we're going to be doing our plus or minus our value. All right. So as we say, the t value, the critical value of the t-distribution with n minus 1 degrees of freedom and an area of a divided by 2 in each tail. So what is student's t-distribution? So what it is, it's a family of distributions. There's another, as we talked about earlier, there's all sorts of different distributions. What we've been focused on over the course of the term, in large part, is what we call the normal distribution with the characteristics of that. The t is just another family of distributions, and the value depends upon what we call the degrees of freedom. All right. Now the t-distribution looks a lot like the normal distribution, which is convenient because basically we're using this. We can use it as a lot of the same stuff we're doing with normal distribution we can apply using the t-distribution. So the characteristics are similar enough that we can use them. All right. So as we look at this is some examples of our t-distributions. So as you can see, here's our normal distribution. This is our kind of arcing curve. And what we'll have is we will have different shapes of the t-distribution depending upon what we call the degrees of freedom. All right. So this is our normal distribution, standard normal distribution. T-distributions, they're also bell-shaped and symmetric, which means they're equal distribution on both sides. But what they'll have is we'll have fatter tails, is maybe the better way to look at it. So as you can see, we're a little bit more, they're flatter, more spread out, more distributed. All right, so once again, because we're dealing with more uncertainty. We don't know quite as, we don't have as much data to evaluate along with our sample. All right, so they are, but they are, they are valid as we're doing this. Okay. Okay, so the way the t-table works, the t-table works very much like what the z-table looked like. All right, and basically what we're going to be looking at is what we call our degrees of freedom. All right. The one thing that's different that we saw between the z-tables and the t-tables, the z-tables, the values that are in the table are probabilities. In the t-tables, the values are what we call t-values. All right. So as you can see, once again, when we calculate, as we calculate this out, what we can do is we can do a lookup based upon what is our, if we're looking in this case, we're looking for a 2 and 0.5. All right, so degrees of freedom, n minus, so n is 3, which is our sample size. N minus 1 is 2, which gives us our 2 degrees of freedom. All right. And then this upper tail area, you say it's 0.1, but it's upper tail, so it's divided by 2. So basically, that's what this 2.90 gives us. Okay, so let's look at we'll look at kind of another example here. There's a lot of figures, but if you just kind of keep the process in our heads. So we look at a random sample size of 100, n equals 100 travel times, has a mean and standard distribution of, this is on the sample, of 110.27, and the sample distribution, standard distribution is 28.95. Given that, we want to create a 95% confidence interval for the population mean. All right. All right, so n minus 1, so our degrees of freedom, which is what we're working with the t distribution. So it's n minus 1, which is 99. All right, which then we use, we do the lookup in the table, which gives us the 1.9842. All right, which then we put it into our formula here. We do our calculation, which gives us the range of between 104. It's going to be, the mean is going to lie between, for 95% of the distributions we evaluate or create, it'll be between 104.53 and 116.01. So that's the population mean. So that's basically our evaluations of getting the population mean by taking samples. Right. And then we also have what we call the population proportion. So kind of the confidence intervals with a population proportion is, we can calculate that by adding allowance for the uncertainty to the sample proportion. All right, so let's look at that a little bit more specifically. So what we're looking at is once again, all these confidence intervals, we have a higher and a lower. Right, so we're basically targeting, we're going to evaluate, we're going to calculate what these endpoints are. All right. As this is the formula for the proportions. We're using the z value, is the standard normal value for the level of confidence desired. P is the sample proportion, and N is the sample size. So once again, we're going to have an overall population of some unknown size. We're going to take a sample of size N, and we're going to calculate the proportion, which is P. So example, this one. So we're going to look at a sample of 100 people, and our calculation is 25% are left-handed. So what we want to do is we want to create a 95% confidence interval for the population proportions of left-handed people. All right. So our calculation here is so we have 25 are left-handed. All right, so we're going to create 95%. So it's 25 divided by 100. And so so we'll do is we take our sample and our results, 25 divided by 100, 0.25. All right, plus or minus 95% confidence interval is 1.96, so it's plus or minus 1.96 plus our factor we're calculating here. All right, so our estimate of the population proportion for left-handers is between um, 0.1651 and 0.3349. So our interpretation of that is we're 95% confident that the population proportion of left-handers is somewhere between 16.51 and 33.49, as you can see. Once again, we're not saying, what we're saying is that how we interpret this is, that proportion, that, 16.51 and 33.49 is the high-low ranges. It might not actually contain the real proportion. It might not it might carry the real proportion number. 95% of the intervals formed from samples of size 100 will. All right, so once again, understanding, one thing is to calculate the information. We get the numbers, but then it's also the interpretation of the numbers is what we're looking for. All right, so that is really what we've talked about with Chapter 8. So it's really about this idea of being able to develop a confidence interval for the mean and population of an overall population, by using samples. So that's Chapter 8. Now, Chapter 9, so we wrap up here. So Chapter 9, we're talking about what we call one-sample tests. So we're going to talk, so in this case, we're going to talk about the hypothesis testing. And we're going to use something called the p-value approach to hypothesis testing to test a population mean and a population proportion. Because once again, we're dealing with uncertainty, and the way we compensate for it is we have we apply a level of discipline around how we frame the question and how we evaluate the answer. All right, so we're not going to do these calculations and say, okay, this is what this number is, because we don't know that. All right. And the framing, the hypothesis and hypothesis testing becomes a means by which we can, state, with degrees of confidence that this is what the potential outcomes would be. So hypothesis, we talked a little bit about this before. It's a claim or assertion about a population parameter. So we will have we can establish a hypothesis around the population mean. Or we can also have a hypothesis around the population proportion. All right, so once again, it's the difference between populations and samples. So as we're doing this, we have something we call the null hypothesis as a starting point, which is so we state the claim that we're going to test, which, what it does, it represents the current belief in our situation. All right. And so we'll say, we'll use as an example for a null hypothesis, population mean age is 30. The way we would represent that would be H0, population mean is equal 30. One of the things to remember about this when we're looking at the null hypothesis, we're using, it's either going to be an equal sign or a less than equal to or greater than or equal to as as what we're going to do from our qualification. It's either equal to a value, less than or equal to a value, or greater than or equal to a value. Right. So here's the process. There's a process around this. So what we do is we're going to assume that we're going to establish the null hypothesis, and we're going to assume that it is true. So as we say here, it's you're innocent until proven guilty. All right. Then what we're going to do is we're going to gather evidence, which is, as we've talked about, we draw samples, evaluate the samples. And then finally, what we'll do is we will evaluate if the evidence supports or contradicts the null hypothesis at the end. All right, so pretty straightforward. All right. Now we have what we call the alternative hypothesis. Null hypothesis is H0. Alternative hypothesis is H1, which is the opposite. So the opposite, so we'll say in case here, population mean is not equal to 30. Right? We're not saying it's greater than or less than. It's simply, the uh, the opposite. So if our hypothesis is greater than or equal to, um, the alternative hypothesis is not that it's less than, it's just that it's not greater than or equal to. So, generally, we describe the alternative hypothesis as what we're trying to prove. So there's a couple things, kind of as we're looking at this, is what we call um, the risks we have associated with decision making using this hypothesis testing. So we have a type 1 error, type 2 errors. Type 1 error is we reject a true null hypothesis. Or, you can look at this, think of this as being a false alarm. All right. And what we do is we associate a probability of a type 1 error, called the level of significance of the test. We set this in advance. The researcher will establish this as a stake in the ground as we're going into this. Type 2 errors is a failure to reject a false null hypothesis. Right, so in these cases, this would be we would call this a missed opportunity. All right, and what we have is we associate a probability, of a type 2 error. We identify that and call that out as well. Okay, so we have a chart here. So if we look at our chart, we have different test outcomes. All right, so the decision is either HO is true or HO is false. And then we have our decision, which is we do not reject HO or we do. So a correct decision, confidence is 1 minus our probability of our type 1 error. All right. And then our type 2 error is, basically we do 1 minus probability of a type 2 error. All right, so you kind of read this as a true, either we don't reject it or we reject it. We assume it's true. If we don't reject it, then it will be true. So it's kind of, you have to kind of look at this and think about it, because it's not quite as, like I said, if we say something like if something is greater than or equal to a value, the opposite of that, or our type 2 decision, is not that it's less than, it's just that it's not equal to. All right. So these are the potential outcomes we can have that we would want to consider. All right, so we have a couple different ways of doing our hypothesis testings for the means around this. One is going to be, once again, situation where we know the standard deviation, and the other one is we don't know the standard deviation. If we know the standard deviation, we can use the z-tables and the z-test, and if we don't know it, we'll use the t-tables, student t-table. All right. So our p-value approach, the testing. Um, so we're looking at this: the probability of obtaining a test statistic equal to or greater than the observed sample, given that H0 is true. So we want to know. So basically, we will kind of establish our baseline, all right, of H0. And then what we'll want to do is we'll calculate this p-value, which is the probability of getting that it will either be that it will be true. We'll say the p-value here is a term we call the observed level of significance, or it's also the smallest value for which H0 could be rejected. So, how do we do a evaluation, or how do we make decisions around this? All right. So if the p-value is less than our value, well, we identify our probability here, we reject H0. And if it's greater than or equal to, we don't reject it. All right. So to remember this is going to be kind of a rule of thumb here. If p-value is low, then HO must go. All right. So that's a kind of a little ditty there you can use to kind of provide guidance for situations. But really, what we're doing is we're evaluating what is the lowest value that we could use that could be there that would that we would make a decision to reject H0. And if it's less than that value, if the p-value is less than that value, then we reject H0. So here's our process. So here's our, this is, as I said, the idea behind this is to say, we map this thing out as a fairly well-defined process, and the structure is what we lean upon when we're, using this in our decision making. You're framing this out as a basis to make a decision, or input to make a decision. All right. So number one, define both the null hypothesis and the alternative. And so you define the null hypothesis and define the negative, the opposite of it, which is our alternative. We want to choose the level of significance and the sample size. All right, and then this level of significance is really a number we pick based upon what we think is the relative importance of the risks of either a type 1 or a type 2 error. Then we will determine our test statistic and sampling distributions, collect the sample data, do our calculations, compute the value of the test statistics and the p-value, and then apply it, and then basically use that as the for the basis of our analysis. And then we'll make our statistical decision and state the managerial conclusion in the context of this theory, claim, or assertion. All right. So once again, it's we're fencing in. Part of this analysis is we're fencing this, or what we're going to do and what we can state about something. We're fencing it in, performing this, basically using the sample to create like an experiment, and then use that as the as the basis to either accept the hypothesis or reject the hypothesis. So if the p-value that we calculate is less than our value or level of significance, then we're going to reject H0. We'll take an example here. Another, these things we look at the theory, but then we look at kind of the practical application. So here's our practical application. So we say there's a claim: population mean age is 30. So what we want to do is we want to create a population. We want to create a null and alternative hypothesis. So in this case, it's going to be um, population mean is 30, and the alternative is going to be population mean is not 30. Right? Not greater than, not less than. It's not 30. And then what we want to do is we'll go through and we'll say, okay, what's our level of significance, and then what's our sample size. So we're going to say, okay, our level of significance is going to be 5%, 0.05, and our sample size is going to be 100. All right. So, what we're going to do, we in this case we know if we look at our information here, you know, if we know the standard deviation, if we in this case we're going to assume it's known. This is a z-test. We're going to collect our data, compute the test statistics and the p-value. All right, so we're going to do a z-value. So I look up in the z-table. P-value is 0.0456. Then what we're going to do is we're going to state the statistical decision and the managerial conclusion. Right, so the p-value is equal to, so in our calculation is 0.0456, and since what we said was our level of significance is 0.05, it's below that, we reject it. So what that means is that there is sufficient evidence to conclude that the mean age is not 30. And once again, as we said, or as we said earlier about standard deviation, do we really know the standard deviation? In the real world, probably not. All right, so so a lot of times we will end up using we'll use the student t-table approach, all right, which basically means that what we'll do is we will take the um, calculate the standard deviation of our sample and then use that as the approximation of our standard deviation of the population. And whenever we do that, what we do is we change the table, so we use a t-table, not a z-table. All right. So if we don't know the standard deviation and we're going to use the sample deviation, this becomes a t distribution as opposed to a z distribution. But everything else we do is the same. So we have what we call one-tailed versus two-tailed tests. One-sided, two-sided. Once again, because what we're doing is we're dealing with this normal distribution, this normal curve, and what we're interested in is what's going on in the tails. All right, so we can do what we've been talking about up to now has been all about two-tail tests, but we can also do one-tail test. So we do one-sided p-values. Using what we call the p-value approach to hypothesis testing. Now, what will happen is, depending upon the program you use, there's a lot of, you can either use Excel, you use whatever. If it generates a two-sided table or two-sided value, the way you deal with that is you divide it by 2. It'll tell you it's in the 1. All right, and jump will actually goodness about jump is it actually lets us do either two-sided or one-sided p-values. So we talked about, so we were talking about doing this for the mean. Once again, so the other thing we had talked about is doing the same thing for a proportion. So if the data is categorical, remember we talked about our categorical is uh, the data type around. We're talking about characteristics. The population is what we call a proportion, the population proportion. Right. And then if when we're looking at the proportion versus the mean, if we're looking at the population proportion, use the z test based on the z distribution to test the null hypothesis. And it works the same way. So basically the same approach, we use the same approach, um, as we were talking about earlier, we will use the exact same uh, approaches for the proportions. Right now, one of the things that's kind of interesting, especially when we're looking at statistical, is this question of whether the difference between something being statistically significant versus practical significance. Um, and what happens is a lot of cases, a lot of situations, statistically significant results, as we say, as we reject the null hypothesis, is not always the most practical approach. All right. So, it's more likely to happen when the sample size starts getting very large. Um, you know, so as we say is, practically important results might be found to be statistically insignificant as we get to uh, larger, larger sample sizes. Or excuse me, let me get this right. So if we have large sample sizes, statistically significant results are not always uh, of practical significance. So the larger the sample sizes, it's not quite as important. Whereas, um, as we get a smaller sample size, we will find ourselves, being able to failing to reject the null hypothesis when the sample size becomes smaller. Mm-hmm. So finally, just to wrap up here, you're talking about some of the work around hypothesis testing, and using what we call the p-value approach to hypothesis testing to test for both the population mean and for the population proportion. And that is it for chapter 8 and chapter 9.